or a service. So accordingly, the recommendation system can be developed. This is one of the important applications where IR is effectively utilized. And then next one is a question answering system. We all know that Quora is a very good platform for interacting to get an exact answer for a particular system, particular question. So here for that, that is one of the important application that will come under the information retrieval. And another important thing is an email spam filtering. So nowadays there are many number of spam mails are coming to our location. Okay, so how to differentiate good mail from the spam mail? So for that application can be developed. And even the multimedia information retrieval. So large number of videos are being processed YouTube. If you take a video YouTube, there are many number of videos are available. How those kind of videos are retrieved? What kind of technique is used for retrieving the video with respect to the YouTube applications? Even with respect to the image also. So there are a lot of images or these kind of things are very commonly available in the Google search engine. So for that multimedia information retrieval system is applied. And then coming to the information visualization, it is one of the important area where the results given by the system should be in a graphical manner. So in the best way the result has to be presented to the user. So for that information visualization technique is available. And text mining. So how to extract the knowledge. So collection of articles are there, research articles are there. How to extract the knowledge from those research articles. So we can make use of this text mining. For example, plagiarism detection, we need a text mining principles. So these are all the applications that come under the IR. Coming to the architecture of the IR system. So this is an overall architecture of the IR system. So two different things we are here. We are going to involve different types of processes. So the first process what we are going to have is a crawling process. So this is a hidden process that takes place in the many type of search engine, and we need to worry about the index process. And the third process is going to be retrieval and the ranking process. So this is three different processes are involved. So for example, if you take a user, so user is going to interact with the system through some search engine such as Google. So they are going to type a query. The query that is submitted to the search engine has to be parsed. So the query has to be any type of semantical and syntactical error has to be detected and corrected. And if there are a limited number of query terms are available, it has to be expanded for getting a more amount of information from the IR. Okay, so in order to get more amount of information from the IR, the query has to be expanded. Okay, so we need to add some sort of synonyms and many number of contextual informations along with the terms specified by the query. We know that the query submitted by the user is uncertain in nature. They may be vague. So for this, that can be reduced. The vagueness and the uncertainty can be reduced by means of expanding our query. And that will be converted to a form. It has to be represented in a form which can be easily used for further processing. So before getting into the retrieval and the ranking process, so we need deal with an indexing process. So first, if you take the next slide, there is a large repository of information is available with the web. So how how the contents of the web is being crawled. So how we are going to navigate from one page to another page. How we are going to discover the pages, web pages. For that, we need a crawling process. Web crawler. So web crawler will be extracting the or it will be discovering the web pages based upon the URL link. Okay, so if you take any particular Wikipedia website, there are many number of links to the various web pages. So the crawler will be otherwise called as a spider. Okay, spider. So the spider is a software tool which is used for extracting the web pages from the World Wide Web. So that is the crawling process. So the crawled pages are being analyzed. Okay, and then it will be stored in a form of a repository. So repository and whatever the document that is available. Okay, so that will be retrieved and it will be represented in a repository. So this particular terms are the content available with the web pages will be properly indexed by means of the indexer. Okay, so what are we know that the documents may be having many number of terms, many number of vocabularies. So those vocabularies have to be indexed in a proper way. For that, we need an indexing process. So the terms which are very much important. Okay, so what are all the terms that are important with respect to a document collection has to be stored in an index structure. So as far as IR is concerned, we are going to use an inverted index as a index data structure for storing the terms, vocabularies or terms in the document. So that terms whatever available in the collection will be stored with respect to the multiple inverted index may be developed, and it will be stored in the form of an inverted index. So once the information is properly represented in an inverted index, it can be used for retrieval. Okay, so the retrieval and the ranking process will get the information that is available in the index, and it will apply some sort of ranking algorithm. Okay, there are many number of ranking, retrieval and ranking algorithm. For that, we are going to discuss with the models, IR models, especially meant for retrieval and the ranking method. So some type of IR models are applied for retrieval the terms that is available in the web, and it will be ranked, and those documents will be given as a result to the user. Okay, so these kind of documents will be given as a result set to the user. So this kind of process is going to be done with respect to the IR system. See, these are some of the subcomponents we are involving with respect to any generic IR system. Coming to the inverted index. Okay, so inverted index. So inverted for any index process. So we need to create an inverted index. So we all know that what is index. So normally index is used for providing a fast search and retrieve of data. So normal data structure we have discussed about the indexing. Okay, so here we are using an inverted index. So this is one of the data structure that is used in the case of IR system. So any indexing is nothing but a word-oriented mechanism. Okay, especially to speed up the searching task. So when we want to fast give the response time of the query has to be minimized. So the searching task should be speed. Okay, it should be fast enough. So for that, the indexing is going to support. Why we are going to inverted index? Normal index, if you take, we are see this particular diagram. Normally, when we want to store the documents, so the document will be having a collection of terms. So we know that any particular web document, if you take, it will be having a collection of terms. So it will be represented in the form of a document term matrix. It is an original index. So any document is being represented by means of collection of terms. So a document D1 will be having a cosmonaut. It will not be having an astronaut, so 0. So the moon will be present in the document 1, car will be present in the document 1, truck will be present in the document. This is a general representation of index. So we are going to call this original document view as a document term matrix, but this will not be supported with respect to our IR. Instead, we are using an inverted view. Why? So instead of representing a document by means of terms, we are going to connect for each term what are all the documents associated. So that is nothing but your inverted view, or we are going to call that as a term document matrix. So what are all the documents which are being associated with each and every terms is going to be represented in a form of an inverted index. So if you take this particular inverted index, so two different things, components are there. Two different elements we have to worry. One is nothing but the vocabularies. So vocabularies are nothing but the terms available in the document collection. Okay, so what are all the terms available with respect to the document? We have to list all the things as a vocabulary and posting list. So we are going to have a posting list. How many number of documents containing that particular term? So that is nothing but a posting list or occurrences. So the cosmonaut is going to be a term which is available in the document D1 alone. It is not available in the document D2 and D3. So only one document is associated with cosmonaut, and number of occurrences is 1. So this is nothing but a posting list. So this is going to be a index, inverted index we are using. See the thing, if you take a document collection like this, so there are 4 number of documents given to us. So we try to create a term document matrix from the collection of documents. So we try to find out what are all the vocabularies available in this particular collections. So there are many number of terms are there, and more number of terms are repeated in nature. So we try to create an index structure is like this, inverted index structure like this. So we try to list all the vocabularies available. Okay, so what are all the possible terms available we want to list, and then in how many number of documents each and every terms are available, you specify that particular value. So 2 is a term which is available in 2 documents. For example, 2 is available in the document D1 and document D2. It is not available in D3 and D4. So you put like this. So similarly, you put for every terms in the corpus. So we are going to call this as a corpus, documents as a corpus, and different types of terms, and along with that we are going to associate the in how many documents the particular term is available. Okay, and then for each and every document how many number of occurrences are there you have to specify while constructing an inverted index. So for example, if a document D1, if you take 2 is occurring 4 times, so you put, so if you take a document D1, 2 is occurring 4 times, so you put 4. Similarly, in the document D2, 2 is available in 2 times occurring. So in the D3 and the D4, there is no 2 is available. Similarly, you populate all the informations with respect to the term document matrix. This is a very simple view. Okay, so this can be written like this also. So we can also write this representation. We can represent inverted index in a form of this manner. So here also, instead of representing the instead of storing all the values, so here we can represent it in a form of a list, how it is given. So number of the 2 is available in 2 different documents, you put that, and then in the first document how many number of times it is available, 4 times. So in the document 1, this is nothing but a document ID. How many number of times occurrences? 4. In the document 2, number of occurrences is 2. So this is nothing but a posting list. So we are going to say the posting list. Each and every term is associated with the posting list, storing the document ID and how many number of times the particular term is occurring. Because if you create an index in a proper manner, then only it will be helpful for effective ranking and retrieval. Hence, the inverted index should be properly designed. Able to understand the concept. So here we are inverted index. What we are going to tell is a term document matrix. Okay, so another complex version of inverted index is nothing but nowadays Google search engine makes use of this full inverted index because there are a lot of discrepancies with respect to the normal inverted index. So we need to worry with the full inverted index. So the full inverted index is normally meant, normal inverted index is not suitable for answering a phrase queries. So phrase queries are very, very important thing. So when we want to search with respect to the phrase, or proximity queries. Proximity queries are, we are going to, the query terms are somewhat related with each other. Okay, the closeness of the terms in the query. So they may be belonging to the same type of a domain or something like that. So this kind of proximities queries and phrase type queries will not be solved by means of the basic inverted index. So hence we need to go with the full inverted index. Nowadays, your Google search engine is going to provide an ad hoc search. Okay, for developing an ad hoc search, it has to support a very complex inverted index. For that, this full inverted index is being used. So see here, if you take this text like this, so there are many number of terms are there. So here the position is given. Here in the full inverted index, we are going to involve the position. For some application or for some model, information retrieval model, we need to worry with the position, not only the occurrences and in which document the term is available is not only enough. So for processing the phrase queries or some type of proximity queries, we need to worry with the position where that particular term is available. So we need to worry with the position. So in is in the first position, theory is in the case of fourth position, and there starts from the 12th position. Likewise, we try to find out the position where the terms are available. So while writing the occurrences, we try to write also the position. We are also representing the position. So full inverted index, if you take between starts in the position 35. So you try to incorporate the position.
Okay, difference starts in 24th position. So you write like this. Theory occurs 2 times. Theory occurs in the 4th position as well as 43 position. So you generate the list like this. So this is one type of a complex inverted index. See here, it's a very complex. Whenever there are multiple documents, so multiple documents are available. So the previous example, we have taken 4 different documents. The number of occurrences of each terms are given. So 2, if you take, it will be available in the document D1 and D2. So total number of documents is 2. And occurrences, so in the first document, how many number of occurrences? 4. In the, okay, and then position. So first position, 4th position, 6th position, 9th position. These quantities, this list represents the first document, number of occurrences and position where the particular term appears. Similarly, in the second document, how many number of occurrences? 2. So if you take a 2, there are 2 times the 2 is available. So you put as a 2, and then in which position it is available. Okay, in the second, which document? Only in the document D2. Okay, so document D2, so you specify the document ID, and then first position and 5th position. First and 5th position, 2 is available. So this is very complex inverted list we have to prepare. So nowadays the Google search engine is go with the full inverted index for developing your search engine. So this is a complex inverted index or full inverted index that is normally implemented. So if the index structure is clearly defined, then only it is easy, only it is used for easy retrieval and ranking. So the indexing plays a very major role. Construction of the index is very major role. There are a lot of methods for constructing the index. So that is that comes under the research. So we want to carry out some type of research. There are many number of tree-like structures. Instead of representing the index in a form of a list, we can go with a tree-like structure. Radix tree is one of the important. It is one of the data structure where the inverted index can be easily represented. It's the most recently developed data structure for representing the inverted index. Then coming to the, see, if you take an index structure, there are many number of vocabularies are there. We want to, here, if you take a 4 document, there are many number of vocabularies are there. So if you take many number of, if you take a corpus is a collection of documents. If there are 100 documents are available in the repository, then we need to worry with so many number of vocabulary terms. So it is very much difficult to store all those terms in the document. So for that, we want to minimize the storage. Okay, so in order to improve the retrieval effectiveness, or in order to speed up the process, we need to reduce certain terms that is available in the inverted index. So in order to reduce those things, we need certain type of index term selection methods. So some of the method is, one of the common method is a stop word removal. So stop words, it's nothing but non-influential words we can take, or otherwise the stop words may be called as a non-informative words. So this non-informative words in no way supports the retrieval process. So we can easily remove those kind of stop words. So the main intention is to filter out those stop words from the index. So it is not necessary to store all the vocabulary, all the terms available in the document in the index. So we need to remove certain words. So those kind of words, non-informative words, we are going to call as a stop words. The general stop words, some of the general stop words are articles, so we can remove the prepositions. So they are not going to helpful for retrieval process. So even in the conjunction words, some pronouns, for removing the stop word removal, we can make use of some natural language processing tool to remove this stop word. There are standard stop words that is being defined. There are standard stop word removal libraries are available. We can make use of those libraries to remove our stop word. And then why we want to remove the stop word? Mainly to reduce the size of the index. So normally we know that 20 to 30% of total word counts that accounts for a stop word. So many number of words that are not value, that has no value. So nearly 20 to 30% of entire document will be occupied by means of this stop word. So that way it will reduce us the index. By removing these stop words, it will reduce us the index structure, and also it is going to improve the efficiency and the effectiveness of the system. Okay, so the searching process may be enhanced.
Okay, so in order to do some sort of text mining system application, that can be effectiveness can be improved. Okay, so that is nothing but a stop word. Another important technique what we are going to use is stemming. Stemming is one of the important technique where there are multiple variants of the same term. Say same term may be represented in many ways. In that case, we are going to ignore or we are going to remove those kind of different variants of the same word. That is, we try to conflate many words into a single word. Okay, stem word. We try to discover a stem word from a given set of words. So there are users, used, using. Simply by removing these suffixes, we get use. Okay, so instead of representing all these four words, we can replace with a single stem word that is nothing but a use. Here also engineering, engineered and engineer will be replaced with a single word that is nothing but an engineer. These are all the stem words. So there is a very popular tool, natural language processing tool, that is nothing but a Porter stemmer. Porter is one of the important application available to remove this kind of stemming words. Okay, which will remove the suffixes, and there is a Porter stemmer readily available. We can make use of the Porter stemmer for doing the stemming operations. And then this kind of stemming will also improve the effectiveness of the IR, and it will also considerably reduce the index size. And then coming to the index search using inverted index. So once we have created an inverted index, so now it is ready for applying some sort of searching. Okay, we try to find out, seek some words from the inverted index based upon the query submitted by the user. Okay, so what are all the terms that is given by the user that can be searched from the inverted index, and those terms, what are all the documents associated with that terms will be given to the user. So that kind of searching facility has to be provided. So there are many number of steps. So whenever a query is submitted to the system, what happens? So in the step one, we are going to provide a vocabulary, how the index is being searched, whatever the terms available in the query. For each and every query term, we have to go with a vocabulary search. Okay, so vocabulary will be stored in a dictionary. Okay, index, it will be stored in an inverted, because inverted index have two different components. One is nothing but vocabulary or dictionary, and along with that we will be having a posting list. Okay, number of occurrences and position. Okay, these kind of information will be associated with the vocabulary. So first thing, we try to go through the index, inverted index, to locate the particular term. Okay, particular query term, we want to locate that in an inverted index, and then finally next step, we try to merge. So if there are more number of documents, so if there are if the term appears in more number of documents, we try to merge all those results, and then we try to find out the occurrences, okay, by means of grouping. Okay, and the posting list, how many number of occurrences are there, in how many number of documents the term is appearing. So we try to go with the merging of the result, and finally we are going to compute this rank. So once the documents are going to be retrieved, once the documents are retrieved, we try to rank those documents. So we try to calculate the rank. Either you can go with the content based ranking, or we can go with the link based ranking. So this content based ranking, normally in the case of different models, makes use of the TF-IDF method. We will be discussing what is meant by TF-IDF method, where the content based ranking, based upon the content available in the document, we are going to perform some ranking. So term frequency, inverse document frequency method is used for content based ranking. And for link based ranking, page rank algorithm. Nowadays Google uses this page rank algorithm for finding out the link based ranking, how the URL is being analyzed, how the link, based upon the link, the ranking is being achieved. For that, a page rank algorithm is used. Google uses this page rank algorithm for retrieving the web pages. Okay, so that is the thing with respect to the searches using the inverted index. Now we will go to the heart of our topic, that is information retrieval models. So participants, whether you are following my lecture or not, or you are getting very bored. Beginning itself, I told that for all the participants, those who are eager to know about the IR concepts, and those who are interested to carry out the research with respect to the retrieval models, IR, they may be interested in knowing all these concepts. Okay, if you have any doubt, you please ask me. Everybody is clear whatever we have discussed before? Okay, so if you have any queries, you please ask me. Okay, coming to the information retrieval model, as far as today's session is concerned, this is going to be the heart of the topics. Before that, we have discussed some few concepts behind the information retrieval system. And then coming to the models, so what is meant by why we want to develop any model? So for designing a search engine, there are many number of models are available. Which particular model will be suits to our search engine? We have to decide that. So here, any particular generic IR model, if you take, it governs how the documents and the queries are going to be represented. So any document model should clearly define how the documents and queries are going to be represented and how the relevance of the document to the user query. So how the document representation will be relevant to the user query, query submitted by the user. This has to be clearly defined by any particular model. So we have discussed with the architecture of the IR system. For developing any particular IR system, we need this particular model. Every model is a mathematical model, okay, which is clearly indicates how the documents and queries are represented and how the relevance judgment is being decided. These things will be involved with respect to the information retrieval model. So it is going to be a complex process. So one of the important function while designing a model is nothing but a ranking function. So what type of ranking function is being involved? So how we are going to assign a score, okay, but how we are going to rank the documents. So how the documents are going to be ranked. So by means of associating a score to the document, the ranking function is going to implemented. Okay, so any particular modeling, if you take any particular retrieval model, there are two main tasks are being carried out. One is nothing but the conception of a logical framework. So we try to develop a logical framework for representation of documents and the query. That is the first process we have to do. How the documents and the queries are represented, how they are being indexed. Okay, so the documents and the queries are represented and it is being indexed in an appropriate way. And then what kind of ranking function we try to incorporate? Normally the ranking function has to calculate that score for every document. Okay, so the ranking function is used to calculate the score. Okay, so this based upon the score, we try to calculate the similarities that exist between the documents and the query. So some sort of similarity measures should be carried out through the ranking function. So these are the two different measures, two different tasks we have to take into an account while creating any particular model. So now you come into the you come to the information retrieval models. So we know that ranking is one of the important tasks for ordering the documents based upon their relevance to the user query. So the ranking should always reflect the relevance. So the ranking should be appropriate so that it is the document should be relevant to the user query. Accordingly, it has to be ranked. Okay, so relevance ranking. We are going to call that as a relevance ranking. So any particular IR system has to deal with the problem of predicting which documents that the user will find relevant. So the satisfaction of the user is very, very important thing. Whatever the documents are given as a result to the user, they have to satisfy whether the document given in the result set satisfies the information need or not. So that kind of prediction is required in the case of the information retrieval model. So for predicting the user satisfaction level, there are many number of evaluation measures are there, such as precision, recall. These are the some of the evaluation method measures which is used to evaluate the document result along with the user information needed. See this thing, any model, there must be a representation of documents and there must be a representation of query terms. So documents have to be represented in a form of different types of terms, and a query may be represented in different types of terms. They may be indexed, okay, they may be indexed, and these two index terms, okay, document terms and query terms are going to be matched. Okay, so the which have a closer association, we try to find out the similarity that exists between the documents and the query, and accordingly the most probable, okay, so the more similar documents along with respect to the query terms are going to be generated as a result, and accordingly it has to be prioritized which score is high. Okay, similarity score we try to calculate using a ranking function. So the documents with the more similarity score will be listed in first. Likewise, it is being retrieved in a result. Okay, so this is a very general structure of any retrieval model. So if you take the, we are in this session, we are going to deal with only 4 different models. So for each and every model, I'm going to give you a real-time example. Okay, so first one is a Boolean retrieval model. Second one is a vector space model. Third one is a language model, and the fourth one is a probabilistic retrieval model. So these models are commonly used for developing any IR system. So if you take a general representation of this quantities of IR model, so it is common to any type of model. There are certain parameters are there. So we need to discuss with several parameters with respect to irrespective of any type of model. So D, what is meant by the capital D denotes. So capital D, we are going to call that as a set of documents. So we are going to call the logical view of documents or a corpus. So we are going to call the capital D as a corpus. It is a collection of documents. And Q is going to be a logical view of a user query. Q is going to represent the queries that is submitted by the user. So we are going to have 2 different representation, and F. F is nothing but a framework. Okay, it is nothing but a function. So that will be modeling documents and the query. So some type of matching. Okay, some type of matching. So that is going to be provided by means of a framework. So the framework for modeling the document and the query has to be represented as a F. And finally, the ranking function. So the ranking function, the relevant document. Okay, so the relevant document has to be retrieved by means of the ranking function. So that is given as R of QI. So your query terms. Okay, I denotes the term. Okay, and D denotes the document, and J denotes the document ID. Okay, so we are going to find out the what is the ranking relevant document that is retrieved for the user query. So that has to be decided by means of a ranking function. So these are all the quantities that may be helpful for developing any IR models. So if you take this particular view, okay, so there are collection of documents that may be represented as a document logical view, that is nothing but a DJ. So DJ represents the document D1, or it may be a document D2. Any particular document we are going to have. And then query. So for each and every term in the query, we are going to have as an I. So how the document 1 is going to be correlated with the query term. So that is nothing but a logical view. And we are going to define your ranking function. So we are going to retrieve the relevant document by means of applying the ranking function. Ranking, this is given. Okay, so document number and the query term. Okay, so here see this real example. So this is going to be a document. There are many number of terms are available. So we are going to represent this document in a form of inverted index. So how it is given as inverted index. So this is nothing but some sort of weight value associated with the term. So if you take a fish as a term, the weight value of the fish is being calculated as 9.7. So this weight value is calculated by means of some type of method. Okay, weight calculation method, some probabilistic method or some method is used for calculating this weight value. So the weight value is associated with each and every term. How to calculate this weight value, we will be discussing in future. So when we are going to a different model, how this weight value is being calculated, we will be seeing. And then different terms, and accordingly, so many number of weights are associated. And then we can also use some sort of query features. So we are going to call this as a topic features or term features. Apart from that, we can also use some sort of quality features such as incoming links. So we can have because your website is dynamic in nature, there are many number of incoming links and outgoing links. So what are all incoming links are there? So we can specify 14 incoming links for that particular web page. And when the data is being updated, so there should not be the IR system should not retrieve the obsolete data. So the data should be consistent and the data should be currently available. Okay, well, the data, okay, accordingly, we are going to have some sort of spatial information or some time series data we want to query. Okay, so 3 days since last update. These are all the additional information that is provided to the ranking function. So your ranking function will provide a framework that gives so many number of items as an input, and it is going to generate the entire score for the document, DG. Okay, so for each and every term, by processing each and every term, it is going to generate the document score. So this particular score has to be generated for each and every document in a corpus, and which are all the document having a high score will be presented to the user. So this is a very logical representation of your model, any type of model. Now we will get into the Boolean retrieval model. So your Boolean retrieval model, if you take, it is based upon the set theory and Boolean algebra. So every model is going to be related with some sort of mathematical concepts. So as far as BAR, that is a Boolean retrieval model is concerned, so it is based upon the set theory, set mathematics, and some sort of Boolean operations are required with respect to constructing the Boolean retrieval model. So first thing what we are going to say that document has to be represented. So any model, if you take a Boolean retrieval model, we want to provide a mechanism for representing a document. So documents are represented by means of set of terms, and queries are going to be represented as a Boolean expression of the terms. So we are going to represent the queries in a form of a Boolean expression, such as a disjunction or disjunction of conjunctive vectors. So we are product of sum. So we all know that how the set mathematics, how the Boolean expression is being represented. So we can make use of the product of sum representation. Okay, here if you take a Boolean retrieval model, every document and our query is treated as a bag of words. So we are going to have a data structure as a bag of words. We are going to call the index as a bag of words, where each and every term of the document has to be collected and stored in a form of a bag. So we are going to call that as a bow method. Okay, here in the case of the bow, we are not worrying with the sequence of words. So we need not want to worry with the position of the word or sequence of the word. Simply the word and the occurrences of the word is being stored in the bow. Okay, so we are going to have a corpus. So that is capital D, the collection of documents over which the retrieval has to be performed. So capital D is represented as how many number of, if you take a data set as an input, so how many number of data documents are available. Okay, we want to represent all the documents. That is nothing but a document collection of the corpus. Next, we want to find out the distinctive words or vocabulary. So we are going to call the capital V as a vocabulary, which consists of set of terms in the collection of documents. What are all the distinctive terms available in the collection? So we represented in a form of a terms, term 1, term 2. So that is nothing but up to entire size. So we want to cover all the terms. So this is nothing but a size of the vocabulary. Okay, and then next one we want to worry with another parameter, that is nothing but a Wij. So here the Wij represents the weight of the term. So any particular term, if you take, we want to associate weight with that particular term. What is the weight of the term in the document D1? What is the weight of the term T1 in the document D2? So we try to find out weight of the each and every term. That is represented as a Wij. Weight of the ith term in the jth document. I represent the term. J represents the document. So that is nothing but a weight. For example, I want to find out the weight of the term apple in the document D1. Then W apple D1. That is nothing but the weight. So we try to associate the weight. So for each term, we want to assign a weight. In the case of the Boolean model, we are going to have a two different possible weight value, either 0 or 1, because it is going to be a Boolean value. Either it must be 0 or it must be 1. For example, if you take a term apple, if it is available in the document D1 means, then the weight value is assigned as 1. If the apple is not available in the document D2 means, then the weight of the term apple in the document D2 is 0. So accordingly, the presence and the absence of the term in the document collection has to be represented in the form of a weight. So the weight value is either 0 or 1. Okay, that is nothing but a Boolean value. So your weight for any particular document, we want to associate all the weight values. What is the weight of the first term in the document DJ? What is the J ranges from 1 to n, because there are n number of documents. Your I ranges from 1 to size of the vocabulary. So what is the weight of the first term in the document J? J is 1, first document, document 1. Likewise, we want to represent the weight value in the various documents. This is a Boolean. For example, if you take a query like this, so if you are Boolean, because we know that in the Boolean retrieval model, any user queries have to be represented in the form of a Boolean expression. Okay, so we try to find out the index terms. Okay, the Boolean expression terms are the index terms, and operators, Boolean operators are and or not. So whatever the terms that is specified in the query, we are going to call those terms as an index term, and they are going to be connected by means of different operators, Boolean operators. For example, so in your query, we have given us a data mining. Okay, so in that case, how the query is being defined? Data and mining. So any particular result should have both the term data as well as the mining and not text. So it should not have a text as a thing. Okay, text should be excluded. Only data and mining should be there. So this is an example for a query. And then we are going to apply some sort of functions over the set of terms and the documents. So here we are going to find out the Boolean relevance prediction. So how the query is being written. So text, if you take this particular example, either here we have used the OR operator, here we had used the AND operator, and here we used the NOT operator. So text or information, any result may have text term, it should have a text or information, but compulsorily there must be a retrieval. The term retrieval should present, but there should not be theory. Theory term should not given in your result. So accordingly, the Boolean relevance prediction query will be formulated like this. See the result. So the result for this particular query is information retrieval, because either text or information. So the result would be information retrieval. The result would be text retrieval, and the another result may be modern information retrieval. So there is no theory. The theory term is not available anywhere. So this is nothing but the result. In this way, the Boolean retrieval model will formulate the query like this. It will represent the query like this. So how the retrieval process is carried out? For any particular given Boolean query, the system retrieves the document. So what are all, in which particular document the text appears? Okay, the term text appears. So we try to scan the index, inverted index, to find out where, in which particular document, what are all the documents associated with the term text. So we try to extract that information. Similarly, what are all the documents associated with the index term information, we have to retrieve. Likewise, we have to find out the documents consisting of these many terms, and it will be subjected to the user. Here, in the case of the Boolean retrieval model, we are not worrying with the ranking function. So here, exact match. So what, since every query is represented in a Boolean form, the exact result will be, exact match will be done with respect to the Boolean model. There is no support for a ranking. This is a very basic principle behind the Boolean retrieval model. So if you take this query, so I have taken a real-time example for a Boolean retrieval query model. Consider a query like this. So if your query is like Brutus and Calpurnia, so Shakespeare novel we have taken. So I have taken this particular example from a Manning textbook. So it was given, the query was represented like this. So if your query is given as a Brutus and Calpurnia, so these two things, these two query terms has to be conjectured by means of an and connecting. Okay, so the query will be represented. So any particular document should consist of both the query terms, this Brutus and Kalpurna. These two terms should be present in a document. That is our query. So what are all the documents? Okay, so to find the matching documents using an inverted index, first thing we want to locate the Brutus in the dictionary. Dictionary is nothing but an vocabulary. In the inverted index, we are going to have a vocabulary that is represented in a form of a dictionary. First, we try to locate the Brutus and retrieve its posting list from the posting file. And then we want to see, we will take this example. For example, we want to each and every query term we have to do like this. So if you take a Brutus, so there are many number of terms available in the dictionary. If you take a corpus, Shakespeare novel, if you take, there are many number of terms available. So we want to represent those terms in the dictionary, inverted index. So first query term, if you take a Brutus, we want to locate the Brutus and we try to extract the posting list. So the Brutus will be available in how many number of documents? Document 1, document 2, document 4. Okay, these many documents, the Brutus is available. So these are all the document IDs associated with the Brutus, the term Brutus. Caesar, if you take, in these documents, the Caesar is a term available. And here we have not represented the occurrences. Just we have the posting list denotes only the document ID alone. Which are all the documents, the particular term is available. California, it will be available in 4 different documents. So we want to extract the posting list. From this set of posting, we are going to call each and every one as a posting list, and the entire posting list we are going to call that as posting file. And then we try to take an individual query. So we have located the Brutus. So Brutus, what are all the documents associated, you try to extract. Calpurnia, what are all the documents associated, you extract. Now you try to apply intersection. So when we try to intersect these two document collections, we will be getting only 2 documents where both these 2 terms are available. So here the result will be given as a document 2 and a document 31. So the document 2 and 31 will be presented to the user by means of your Boolean retrieval model. So there is no ranking. Just we have presented the user what are all the documents in which 2 terms, query terms are available. Just we are provided. So this is a very simple example for a Boolean retrieval model. Another example I have taken. So if you take a document corpus, consists of 4 documents, D1, D2, D3 and D4, and each and every document will be having a set of terms. So for clear understanding purpose, I have taken this example. Please be patient to listen this example because it will be, I have thoroughly discussing about each and every model. Definitely it will be useful for you. Okay. So if you take a document D1, there are several set of terms. Document D2, there are several set of terms. D3, D4. Likewise, we have taken a 4 different documents. There are many number of terms available in those documents. Suppose if your query submitted by the user consists of only 3 terms, that is byte, data, and hardware. We want to represent. In the Boolean model, we want to represent. So your query term consisting of 3 terms means it has to be represented in a form of a Boolean expression. So byte and data and hardware. So any document consisting of these 3 terms has to be retrieved to the user. That is our ultimate goal. Now you create a term document matrix and associate the weight values. So you for the term document matrix, what are all the terms available in the corpus, you try to find out. So totally there are only 4 different terms, five different terms. So you list all those terms, Apple, byte, computer, data and hardware, and you represent all the documents, term document matrix you create. And then if you take an apple, if it is present in document D1 means you put 1, otherwise you put weight value as a 0. So since apple is not present in the document D1, you put as a 0. So if it is available in the document means you put 1, because in our Boolean model you can have only 2 possible values for the weight, either 0 or 1. If the particular term is present in the document, you put as a 1. If it is not present, you put as a 0. Likewise, you populate the inverted index. So the index is like this. Now you process your query. So the first term is nothing but a byte. So what is the value for a byte you take? So the value of the byte is 100, Boolean value you take. So it is present in the document D1, but it is not present in the document D2, D3 and D4. So you take that particular value. Similarly, you take the value for data and then you take the value for hardware. So 1011. You apply the Boolean operator and function you apply. So if you take an AND function, you will be getting a result as 1000. So the document D1 is alone 1. The remaining document D2 is 0, D3 is 0, and D4 is 0. So you try to find out here, based upon your result, we can say easily that only one document is retrieved, that is D1, because D1 is alone is 1. The remaining documents are having a 0 as a result. So you retrieve a D1 as a result to the user. It is a very, very simple concept. So by making use of this index structure, we can apply this Boolean retrieval model to find out which documents may be presented to the user. Here we need not want to worry about the ranking. So with this example, we can say that these three terms are available with respect to the thing. Okay. Likewise, we can have like next one. Okay. Okay. So next model. So I think you will be understood with this Boolean model. Okay. Next we will discuss with the vector space model. So the vector space model is somewhat complex with when compared to the Boolean model. So we are going to have a vector space model. What is an idea behind the vector space model? So what is while creating a vector space, it is very, very important model. This particular vector space model is very important model for developing many number of complex models. Okay, so latent semantic modeling or many number of models are developed with the basis of a vector space model. So the main idea of the vector space model is nothing but the meaning of any document is conveyed by the terms used in the document. Any document, when we want to try to interpret the document, the words, the terms appearing in the document is going to provide a meaning. Okay, any type of keyword searches, this vector space model can be applied. So this vector space model can be widely used in the case of ad hoc retrieval. Google is one of the ad hoc retrieval search engine because it is going to have any type of queries. Any different types of queries can be submitted to the search engine. It can able to retrieve any type of document. So it is ad hoc in nature. So for processing the ad hoc retrieval, we can make use of this VSM model. Here also, we are treating the documents as a bow. Okay, in the Boolean model also, we have treated our document as a bow. In the here also, we are going to treat our documents as a bow. Okay, bag of words method model we are going to have, and here we try to have a space. So we are going to call a specific space that is nothing but a vector space. In this vector space, it is nothing but a two-dimensional representation. Okay, so this particular vector space, there may be a set of documents which may be represented and a set of query terms that may be mapped into this particular vector space. See this particular example, we are going to have a vector space like this. So any particular document is going to be represented in a form of a weight value, and the queries are also represented in the form of a weight values. So the vector is given like this, document vector. So a document vector, we are trying to, what are all the terms available in the particular document, we want to associate the weight value. So the first thing, the weight of the first term in the document DJ. What is the weight of the second term in the same document G? What is the weight of the third term? Likewise, we are going to have the vector space like this. Similarly, each and every term, query term, you assign a weight. So what is the weight of the first term in your query? What is the weight of the second term in the query? There may be n number of terms in the query. We want to represent like this. So the document vector and query vectors are represented like this. This is nothing but your vector space, simple representation of vector space, where document D1 is being represented. So what is the term? If the term 1, number of occurrences of the term 1, we are going to represent a document D1. Similarly, we can have this many number of term 2 is available. We can have any number of terms. Okay, maybe a vector space have multiple terms. If there are multiple terms, we can have many number of dimensions. So for simple view, I have taken only 2 different terms. So the document vectors D1 is represented and document D2, another document is represented, and the query vectors are also represented. So your vector space model will be able to find out the similarity that exists between a particular document and a query vector. Document vector and the query vector, and it is also possible to find out the similarity that exists between one document vector to the another document vector. So we can able to compare the vector values. Okay, angle. So we try to find out the angle between the particular document and the query vector, and then we compare these two angles. If the angles are large, then similarity will be if the angle is large. If the angle is 90 degree, then the similarity will be less. If the angle is 0 degree, then similarity will be more. That is the very, very important thing we have to note. If angle is 360 degree means we can say that similarity score is 1. If the angle is 90 degree means the similarity score ranges from 0 to 1 at any values, okay, any decimal value. If the angle is angle between the if the angle between any two vectors is 0 degree means the similarity will be 1. If the angle between any two vectors is 360 degree means then the similarity will be 0. So whenever the angle is large, similarity score is less. That thing we have to note. That is nothing but a vector space. In the VSM, we can able to find out the similarity that exists between the documents and the similarity exists between the document to the query. Two different similarities we can able to find out. So the very common method what we are going to find out is nothing but a term frequency inverse document frequency method. This particular important weighting method is used to calculate the weight of the each and every term in the document, TF-IDF method. So this TF-IDF method is used to calculate the weight of each and every document terms. Sorry, ma. So once weight has been calculated, so based upon the weight, we are going to rank the documents which are closest to the query. So for calculating the similarity exists between the query, we want to calculate the similarity score value. The similarity, how far the document vectors are close to the query vector. So we try to calculate the similarity score. For this, there are many measures are available. In the vector space model, we are using a cosine similarity for calculating the similarity score. So we will be seeing an example. Okay, so if you take a term frequency method, so what is meant by term frequency inverse document frequency? So we want to have here the term frequency and inverse document frequency have two components. One is the term frequency, another one is an inverse document frequency, and multiplying the term and the inverse document frequency, we will be getting a weight value. Okay, so that is given. Term frequency is what? So term frequency is nothing but the weight of the term I in the document DJ. So I is nothing but the I ranges from 1 to size of the V. That is how many number of terms are available in the document corpus. How many number of terms are available in the documents. Okay, we are going to have. So for each and every ith term in the jth document, okay, so we try to calculate the weight. So this is simply calculated as FIJ, frequency of the term I in the particular document DJ. So how many number of times the term T appears in the document DJ, we are going to calculate. That is nothing but a term frequency. So TF of IJ is given as FIJ. That means frequency of ith term in the particular document J. Okay, so where I ranges from 1 to n. N number of terms are there means then I ranges from 1 to n. So what is the frequency? We try to calculate for each and every term how many number of times it appears in the document. That is the thing. So we can able to normalize. So if the frequencies are more, then it is very difficult to manage. For that, we can able to normalize the term frequency by means of dividing that with the maximum frequency value. Okay, so here how many number of times the term appear in the document, the ith term appear in the document J is divided by maximum frequency. So what is the frequency of other terms in the corpus? So we have to take the dictionary. In the dictionary, there are many number of vocabularies are there. So what is the maximum frequencies of other term? So we want to offset like this. So we want to divide our frequency with respect to the maximum frequency. We will be getting a normalized term frequency. This is a term frequency, and then we are going to calculate the inverse document frequency. This is one of the important measure. Especially it is used to diminishes the weight of the term that occurs more frequently. So term frequency will be giving weightage to the more occurrence term. So which particular term is occurring many number of times will be given a very importance. Okay, it will be given an importance, but that will be diminished. That will be offset by means of your inverse document frequency, it will try to diminishes the weight of the term that occurs frequently. At the same time, it increases the weight of the rare term. That is, we have to find out this kind of correlation. So the frequently occurring term will be diminished. The weight of the frequently occurring term should be minimized. At the same time, we have to increase the weight of the rare terms. So that kind of facility will be provided by means of inverse document frequency. So the formula for inverse document frequency is nothing but a log of capital N divided by DFI. That is, N is nothing but total number of documents present in your corpus. Okay, divided by in how many number of documents that particular term appears. So we will take it in, divide that between from that of the document frequency. We are going to call this as a document frequency. In how many documents the particular term appears. So that is nothing but a ith term appears. That is given like this. So once IDF is calculated, we want to calculate the weight value. So the weight value of the weight of the ith term in the document DJ is being calculated as a term frequency of ith term in the jth document multiplied by inverse document frequency of ith term. So we are going to get the weight value like this. Okay, so the weight value denotes the weight of the ith term in the jth document, where I ranges from 1 to size of the vocabulary and j ranges from 1 to n, that is available in the capital D, that is corpus. Okay, we will take a real-time example for a vector space model. Suppose if we are given with 3 different documents I have taken here. Document D1 consists of so many number of terms, and document D2 and document 3. Now I have to calculate the term frequency. So here we are going to have a I have taken different types of documents, document D1, D2 and the D3. So here I have represented as a document term matrix. Don't worry about that. Just for representation I have given. So the 2 is a term that appears 2 times in the case of document D1. So in the document 1, 2 is occurring 2 times. So 1, 2 times. But T is occurring 2 times in the document D1, 1, 2. So the number of me, there is no, the term me is available in the document D1. So you put 0. Here we are not representing a Boolean value. Instead we are calculating the occurrences of the term. So similarly, you have to find out the frequency of each and every terms in the documents. You have to find out. Next we want to calculate the inverse document frequency. So inverse document frequency you try to calculate. So it is nothing but the log capital N divided by DFI. So capital N denotes the total number of documents in the corpus. So the capital N is the totally, we have taken a 3 documents, so you put 3. So document frequency. So we have calculated 2. If you take a term 2, how many documents the 2 is available? It is available in only 1 document, so you put the document frequency as 1. T is available in 2 documents, you put 2. Me is available in 2 different documents, document D2 and D3, you put as a 2. Likewise, you try to calculate, find out the inverse document frequency, you apply it in a formula, log 3 by 1, you will be getting some values. So this is nothing but the IDF values for each and every terms. Now you calculate the weight value. So weight value, you multiply the term frequency value and inverse document frequency values. So the weight value for the weight of the term 2 in the document D1 is given as 1. Okay, because 2 is value is how many number of times the term frequency of the 2 is 2. Sorry, no. 2. Okay, how this 1 comes means 2 divided by maximum frequency. So the maximum frequency is 2. So 2 divided by 2 equal to 1. You multiply the term frequencies. You know that why we are here. Term frequency is given as 2, but I have given 1. Why means here we want to use the normalized term frequency. Normalized term frequency is nothing but Fij divided by maximum frequency. So Fij is 2 divided by maximum frequency is 2. So 2 divided by 2 equal to 1. We will be multiplying with the IDF. We will be getting this value. Similarly, you try to calculate the weight value for each and every document. So for the document D1, what is the weight value of each and every term? In the document D2, what is the weight value of each and every term? And for the document D3, what is the weight value of each and every term? So you try to find out this weight value. Now, once weight value is generated, you represent it in a form of term document matrix. So now in the VSM model, we are going to use a term document matrix as an inverted index. Now you populate all the weight values in the term document matrix. See here how the document weight value I have taken. So each and every terms in the collection, you put 2. What is the weight value for the document D1? So the weight of the term 2 in the document D1 is 0.477. We have calculated previously. Similarly, you put for, so there is the weight for the term 2 in the document D2 is 0. Document D3 is 0. So there is no term available in the D2 and D3. Likewise, you put all these values in the inverted index. So this is an inverted index. We populate the index with respect to the weight values. Have you, are you clear, students, here, participants? Okay, next we will see with the retrieval. So once inverted index is created, now we try to calculate the similarity measure. So how we are going to retrieve? We want to perform some retrieval using a vector space model. We try to calculate the similarity measure. So you represent all the weight values in the vector space. Okay, so you represent all the weight values in the vector space, and then you try to find out the similarity measure. Even though there are many measures are similar, any similarity measure is a function that computes the degree of similarity between two vectors. Okay, so it has to find out the similarity between the document vectors and query vectors. So very common similarity measure what we are going to use is a cosine similarity. So cosine similarity of dj comma q is equal to dot product of a document. Okay, so the dot product of a document vectors and query vectors divided by magnitude of document vector and query vector. This can be rewritten as summation of I is equal to 1 to t. Okay, how many number of terms, maximum number of terms available, that is product summation of weight value, weight of the ith term multiplied by in the document dj, and weight of the same term in the query I. So the same term we have taken, but we have multiplied the weight of the term in the document and weight of the term in the query. Both these vectors has to be multiplied. These two weight values has to be multiplied, divided by, you put the square root of summation of the WIG, weight value of the document weight value. Okay, ith term in the document. What is the weight of the ith term in the document squared, and the weight of the ith term in the query. So we have taken like this. So if the angle between 0 degree means more similar, as already I have told that if the angle between two vectors are 0 means then more similar. This will generate a similarity. Okay, okay. And then if the angle between these two vectors are 360 degree means then similarity score is 0. So for this we have developed this algorithm. So directly we can calculate the similarity by means of cosine similarity. See, I have taken another example for this. Query is given as gold, silver, truck. So your document is given as 3 different documents I have taken. Total number of documents is 3, and idea of the formula we have written. You create a term document matrix. So you write all the terms. So I have not removed any stop words or stemming. I have not applied. Simply I have represented all the terms. So each and every term you have represent, and what are all the query terms present? You put that only alone. You put those terms alone. So what are all the query terms? Gold, silver, truck. So you put 1 for gold, you put 1 for silver, and you put 1 for truck. The remaining terms you put 0. And then if the term is available in the document D1 means you put 1. Otherwise you put 0. Likewise, you find out what are all the term frequencies. How many number of times the term appear. For example, silver appear 2 times in the document D2. So you put as a 2. So if the silver is a term that appears 2 times in the document D2, you put 2. Otherwise you put 1 or 0. And then you try to calculate document frequency. So document frequency, in how many number of documents the term appears. So the term A appears in all the documents. So you put 3. It is arrayed appears only in 2 documents. So you try to find out the document frequency. Now you calculate the the IDF. So suppose if we want to calculate the IDF, we want D divided by DFI. So you put DFI, we have already calculated, that is nothing but 3. Okay, denominator you put, and the total number of documents is 3. So you have to calculate this value, and you apply the log. You apply the log, and you try to find out this IDF value. So we have found out this IDF value. Now you try to calculate the weight. You multiply the TF value and IDF value. That is for each of our query. Okay, so here if the term is ith term, query term, you try to calculate. Similarly for document term, you try to calculate. For the query, what is the weight of the term I? So what is the weight of the term A in the query? 0. What is the weight of the term gold in the query? So this is nothing but your weight. So what is the, because already I have written for this query 1. Okay, so we multiply this with the IDF value. Okay, so we will be getting 1 multiplied by 0.1761 because IDF is a global value, but a TF is a local value. Okay, so you multiply 1 with 0.1761, you will be getting like this. Similarly, silver. Silver is a query term that is available with respect to the document D2. So silver 1 into 0.477 you put, and then 1 into 0.176. Likewise, you put for each and every document. So this is nothing but the weight value. So what are the query values? Only 3 terms are there. The document, how many number of values are there? In the document D1, there is a shipment of gold damaged in a fire. These are the terms. So 1, 2, 3, 4. We have taken like this. So likewise, you put for each and every documents like this. So the weight values are calculated like this. And then once weight values are calculated, you apply the cosine similarity. So cosine similarity, first denominator you have to find out, that is the root of wi squared. Okay, that is weight of the term I in the jth document. So document D1, D2, D3, you put like this and the value. Okay, and then you provide, you sum all these values, you'll be getting this value. Okay, you apply directly with this thing. Okay, so for each and every document you apply all these weight value wij, that is the weight of the term in the document D1. So we have taken only a 1, 2, we have left all the 0 terms. Only the term which is occurring in the document D1, you take those terms and you try to calculate this value. And then similarly for the query terms, only 3 terms are available. You take the weight values of those 3 terms from the previous table. You take the values from this table and you try to apply it in a formula. And then you will be getting the denominator value like this. And then in the numerator value, you try to, in the numerator, we are going to have a, what is the cosine similarity value? Wij multiplied by Wiq. Simply, we are going to multiply the weight of the term, document term with respect to the query term. So you have to write some of those terms. The document D1, we have taken only a query term multiplied by document D1. Okay, so you have taken, I have given here the simplified version. If you write thorough everything, you will be getting this particular answer. So in the numerator, you try to you substitute the value and you generate the result. So finally, we will be getting the value like this. Cosine angle, the final value we are going cosine of angle D1. So you apply the numerator and denominator, you will be getting the values. So these are the set of the score. This is a similarity score generated for the vector space model. Once the similarity scores are generated, you rank those documents. So the similarity value of the document D2 is high, more when compared to the document D3 and D1. So the more similar, you rank the document in the descending order. Okay, so the document D2 is ranked first, and document D3 is ranked second, and the document 1 is ranked as a third. So this particular results will be given to the user. Okay, so this is nothing but your vector space model. So the vector space model ranking will be there, and it is not necessary to provide an exact match. Some relevant match is being provided with respect to the vector space model. Here we are going to, we had used TF-IDF method for calculating the weight, and for a similarity measurement we used the cosine similarity. So there are other similarity measures with respect to the vector space model, inner product method, Dice coefficient. These are all the sum of the formulas. Okay, there are many number of similarity scores are available for in the case of the vector space similarity, but we had applied this cosine similarity, Jaccard coefficients. So these are all the sum of the similarity measures available to find out the similarity that exists between the query and the documents. Okay, now 2 different models we have seen. Another one is a language model. So please, if you have any doubt, you please interrupt me. Okay, so we are thoroughly seeing about the concepts. Okay, coming to the language model. So language model is one of the model which is normally used for, especially for text to speech conversion. Okay, so in the case of the real-time applications such as speech processing, when we want to convert text to speech, okay, so most of the application, there is a requirement to convert the text to speech. In that case, we can apply the language model. So the main goal of the language model is to assign the probability to the sequence of the words by means of the probability distribution. So the language model is based upon the probability distribution function. So we try to find out the probability distribution function. Okay, so it is one of the mathematical technique we want to apply. So rather than using a vectors and algebraic method, here we are using a probabilistic based method for language modeling. So if one word is given, what is the sequence of word that is more likely to occur? So we can able to find out what are all the probable words for the particular word. If the bank is a term word given means, we can able to find out what are all the probable word that may appear. Okay, along with that bank, we can able to find out that probability by means of this language model. And the model will also try to predict the output that has never occurred before. So some sort of prediction may be done. So if the particular term that does not occur means, we can able to discover the terms. Okay, the term need not be explicitly specified in the query. So it can be easily extracted by means of a language model. See, the finite state automata, if you take, it is a very simple model for representing a language modeling. So I have taken two different terms, that is I and wish. The initial state they are represented as a term I, and the final state I have represented as a wish. So the model will be generating, this particular model will be generating a text like this, I wish. So the final state is going to be a wish. So once this cycle will be continuing. So many number of times the process will be continuously executed, but the final term should be wish. Okay, so it is a final state. Okay, so I can generate these many things. I wish, 2 times, 3 times, 4 times, 5 times, n number of times I can generate. It is very, very simple model for representing a language. Okay, so coming to the probability distribution function, so you may be knowing about what is a probability distribution function. So what is the probability of generating any random variable? So that we have to discuss in the case of the probability distribution. So what is a possible outcome? Okay, of a random variable we want to generate. So for example, I have given a collection of objects like this. So some objects are orange in color, some objects are red in color, and some objects are blue in color. So if I randomly pick one object, what is the probability? So if I randomly pick the red color, what is the probability means? The probability of red color will be ranging from 0 to 1. The probability value should ranges from between 0 to 1. Okay, the sum of probabilities of all the objects must be always 1. So we have to know these two things. Okay, the probability value should ranges between 0 and 1, and the sum of the probabilities across all the outcome must be 1. We have to know. So what is the probability of randomly selecting the red color object? Okay, what is the probability? It is represented as the probability of red. Then the probability of blue, probability of orange. So the total probability, when we add all those probabilities, we want to get the result as 1. That is an ultimate objective of this probability distribution function. So for example, what is the probability of red color? So I randomly pick one color, that is, what is the probability of red color means, that is how many number of red colors are present. So 10 number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 objects are red in color. So total number of objects is 20. So the probability of picking red color is how many number of, what is the probability of picking red color? So 0.5. Similarly, probability of picking blue color object, 5 divided by total number of objects. So we will be getting, so number of occurrences divided by total number of objects. So similarly, so the total value will be getting us 1. Total probability I will be getting us 1. This is a very basic principle of the probability distribution function. Your language model is closely related with respect to probability distribution function. So here many number of topic models are created using a language model. So in a Google search engine, if you take any type of search engine you take, we are using only a topic models. So what are all the topic, what are all the documents related with that particular topic, we try to discover. Sorry. A topic in a document or a query can be represented as a language model. So we try to represent whatever the topics available in the document and what are the topics available in the query, we want to represent it in a language model. Okay, the words that tend to occur more often, okay, will have a high probability. So two different things. So if the word occurs many times means it will be having higher probability. If it occurs rarely means it will be having a less probability. That is the thing. Okay. So if you take a movies, so if you take a movies as a document, there are many number of terms that is related with a movie. So here in this diagram, I have shown that different types of topics. So movie is a particular topic. The document relevant to those topics are given in the form of an object like this. So I have not written all those terms here. Here orange may be one of the term. It represents as a term which is related with the movie. This is a term that is related with the movie. These are the terms that is related with the politics. These are the terms that is related with the sports. Likewise, I have to go with this. So what is the probability of the red? So red is one type of term which is related with the movie topic, which will come under the topic movie. So probability of red is equal to 0.5. So you just apply the occurrences divided by total number of objects. Similarly, you try to, for this particular topic, what is the probability of different terms? For this particular topic, what is the probability of this thing? So likewise, you try to find out all those probability. So if you see the probability of this particular term, red, the red may be some term cricket. The cricket may be available in the movie. The cricket may be available in the politics. The cricket is available in the sports. Cricket is not available in the music. The cricket is available in the nature, but it is closely related with the topic sports. This kind of information we are going to take. So if you take a Rajnikant, if you take Rajnikant as an orange color, so orange color represent a Rajnikant, term Rajnikant. Rajnikant will be available in the movies, topic movies, but it will be available in the politics, but it is not available in the sports.